The way we get around this is we split the memory up into two types. We have our main memory, which we build out of dynamic RAM, but we also have a second type of memory, which is actually often built into the CPU as well. Now this is much smaller, but is built out of much faster memory. And this is referred to as the cache. Now the cache is perhaps an old-fashioned English word, but it basically just means a small place where we can store things. So you might use it to store your hidden treasure if you're a pirate, or to store your food for winter. Another example where you might have come across a cache is with your web browser. So the cache on the web browser is used to get around the fact that it takes a relatively long time to fetch a piece of information over the internet compared to accessing something on your local machine. So what happens is, when you go and fetch a page from the internet, the browser will go and get the HTML page, it'll get the CSS files, the images and so on, and it stores or caches a copy onto your local disk that it can then refer to if it needs to get it again. And the idea is that we can get the data from the local copy a lot quicker than it could if it had to go and fetch it from the web server somewhere else in the world. And it's the same approach that is used by the CPU. The CPU's got the same problem. It can talk to its cache on the CPU very, very quickly, but talking to main memory compared to talking to the cache is a relatively long time. So what happens every time it requests a bit of data, it caches a copy locally in the cache built onto the CPU so that when it needs to fetch it again in the near future, it can access it from its local copy a lot faster. There's some other tricks that it can do as well, because the CPU can say, well, actually, if I fetch this instruction, there's a very good chance that I'm going to execute the next instruction and the one after that at the same time. And so what it can do is, rather than just getting one word of memory at a time, it'll say, well, okay, get me the next 128 bytes of memory, and it'll read what we call a cache line, one single lot of 128 bytes from memory into the CPU in one go. The idea being that it takes less time to read 128 bytes in one go than it does to read each 128 bytes individually. But that's down to the way memory actually stores things. So we talked about in the previous video how we would have an address, a binary number that represents each different bit in the RAM chips. But actually, rather than storing it as one big list of bits, it actually stores it as a grid. The address you give it from the CPU gets split up to reference a particular row and a column of that grid to get the particular bit it's interested in. Now, the way the RAM chips are worked, once you've selected a specific row, you can then access each of the columns in that relatively quickly compared to changing to a different row. So if we want to get 128 bytes, if they're all in the same row of memory, then we can access them very quickly and so copy them into the CPU's cache much quicker than if we were having to select different rows at a time. So how big does the cache on your CPU need to be? Well, actually it turns out that you only need a relatively small amount of cache to make a significant difference, because our programs are often sitting in loops, executing the same set of instructions again and again and again, and so if you've got enough to store that loop, then they can be cached and it'll work fine. Or the program's accessing the same block of data and manipulating that in different ways, and so if that will fit into the cache, things work relatively fine. So we don't need that much. You often use separate caches for the instructions and for the data so that you don't remove the instruction that you're interested in to put a copy of the data that you're going to process in there. I mean, you can think about it that you might have a field full of turnips, and so you'd have to go and dig them up, but you might also have a cupboard with your turnips in the kitchen so you can make your stew that night without having to go out into the field. And if you're out working somewhere else, you may even have a turnip in your backpack to eat on the way out.
Second level turnip cache.
Yeah.
Hopefully, by now, you have learned that computers store their state information in chunks of bits called words. These words can be stored in various places such as the RAM, registers, or hard drive. In this lecture, we will learn more about how we store state information in these registers. Each register in a computer is composed of a set of smaller storage units called flip-flops. Each flip-flop stores 1 bit. So, in an 8-bit architecture, each register is composed of 8 flip-flops. Let's take a closer look at the structure of the individual flip-flops. Each flip-flop has 2 types of inputs. The first type is the clock input. The clock input is critical because we want all of our storage components to update at the same time. Consequently, each flip-flop is designed to update once per clock cycle. The flip-flops in this example are called positive edge or rising edge triggered flip-flops. So they will all update whenever the clock signal rises from a low voltage to a high voltage. Certain components that are controlled by the clock, like flip-flops and registers, are called synchronous components. The second type of input is called the data input. This input determines how the state of each flip-flop updates every clock edge. The flip-flops in this example are called D flip-flops. If the input to a D flip-flop is 0 during the rising edge of the clock, then the flip-flop will store 0 until the next rising edge. If the input to a flip-flop is a 1 during the rising edge of the clock, then the flip-flop will store a 1 until the next rising edge. We can recall the value that is stored in each flip-flop at any time from the output of the flip-flop. Keep in mind, though, we can change what is stored in the flip-flop only during the rising edge of the clock. But we can read the value that is stored in the flip-flop at any time. As we said earlier, we can construct an 8-bit register out of 8 flip-flops. I'm going to ask you to use your imagination and pretend that we have arranged 8 flip-flops on the screen, but we're only going to show 4 because of space limitations. To create the 8-bit flip-flop, we need to show the different types of connections that the registers will have. First, all of the flip-flops will share a common clock signal. Second, each of the flip-flops will receive a separate data input. This data input configuration is called a parallel load design. Finally, each of the flip-flops will contribute one data output to the 8-bit register. When we draw the final 8-bit register, we typically do not draw all the internal flip-flops, and we also rearrange the inputs and outputs to facilitate reading. So, in this lecture, I demonstrated the basic functionality of flip-flops, and I demonstrated how we can combine flip-flops to create a register. This process of abstracting the structure of smaller components to create larger components is called modular design. Modular design is one of the most important concepts in computer engineering. You should always look for opportunities to build more complex tools from several
A computer's registers
simpler.
each store the same number of bits. When we want to manipulate what is stored in these registers, the register file will be instructed to send the contents of 2 registers to the ALU. In this example, the registers are 8 bits in length. The ALU will perform a calculation on these 2 values and send the result back to the register file to be stored. We tell the ALU what instruction to perform by sending it a set of control bits that encode a message of what operation to perform. Because the ALU is a combinational circuit, it will perform these calculations immediately. To simplify the diagram, we will use a bus notation where we group sets of wires together and indicate how many wires are in that group. Rather than draw 3 sets of 8 wires, we will simply draw 3 buses. An ALU can perform whatever arithmetic operations that we know how to implement, such as addition, subtraction, multiplication, as well as decrement and increment operations. Bitwise logical operators, such as not, and, or, and others, comprise a list of non-arithmetic operations, such as value comparisons, and setting a register's contents to 0. The details of these operations are covered in another lecture. Suppose that we have an ALU that receives 2 control bits. Because there are 2 control bits, we can encode 4 operations for the ALU to perform. I've chosen 2 arithmetic operations and 2 logic operations for this example. The ALU receives inputs from 2 8-bit registers and sends out 8 bits of information back to the register file. Based on the data from the control bits, the ALU knows which operation to perform. In this situation, the ALU calculates the sum and sends it to the register file. If we change the control bits, we will change which operation is performed. Because this operation does not need an input from B, the B inputs will be ignored. The ALU will send an incremented value of A back to the register file. To briefly introduce the logic operations, we will examine one of the simpler operations, such as the NOT operation. The NOT operation receives only one set of inputs, so again, the ALU will ignore the inputs from B. The NOT operation changes all zeros to ones and all ones to zeros. The NOT operation is applied to each bit in the register individually, otherwise called a bitwise operation. Finally, if we change the control bits again, the ALU will perform a clear operation, which means that we will set the contents of a register to 0. For this operation, the ALU ignores both inputs and simply sends out the value 0. Notice that the ALU is sending out 8 zeros, because all numbers, even 0, are encoded with the same number of bits in a computer. In this lecture, you saw that an ALU receives information from the register file and then performs operations on this information. The control bits encode information about what operation the ALU is to perform. These operations will either be arithmetic operations or
So now let's briefly
bitwise
take a look
logic
inside the
operations.
CPU itself to see how it would process an instruction. As we saw earlier, this is the inside of the 6502 CPU. Let's take away the 6502 wiring and see what's inside the Scott CPU. The first component is the control unit, which is kind of like a captain in the Army. It receives its orders from RAM in the form of an instruction, and then breaks that instruction down into specific commands for the other components. One of the most important components under the command of the control unit is the arithmetic logic unit, or ALU for short. The ALU is what performs all the mathematical operations inside the CPU, such as addition, subtraction, or even comparison like we saw earlier. The arithmetic logic unit has two inputs. We'll label them input A and input B, and assume they are two numbers from some previous load instructions. Now we might want to add those two numbers together. The control unit receives that instruction from RAM and then tells the ALU what type of operation to perform. The ALU performs the operation and then outputs the answer. Sometimes, though, depending upon the type of instruction, the output from the ALU can actually be ignored. For instance, if you have a compare instruction, the ALU doesn't need to output an answer. Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover